So a linearity is a concept that may already be familiar to you. I mean, you've probably heard people describe an equation like y equal mx plus b as a linear equation. And I'll show you soon that that's actually technically not true according to the definition I'm going to give you here. But in the world of differential equations, linearity is a very useful concept, as we'll see throughout the course. The reason for it being so useful is a little hard to motivate until I go through a careful definition of it. So first I'm going to address the definition of linearity in this video, and then if I have time, I'll continue on to show you why it's so useful, but that may come in a separate video if this gets too long. So I'm going to start just by asking a question based on your sort of preconceived notion of linearity. Is the equation y times y prime equal sine of t minus 3t squared linear? And when you answer that, I'd like you to think about which terms or which term in this equation is responsible for linearity or the lack of linearity. So justify it in your head. So I'm going to ask you to just stop the video, think about it for a few minutes, and say to yourself, does the y prime term cause this to be a nonlinear equation? Does the sine of t term cause this to be a nonlinear equation? Does the 3t squared y cause this to be a nonlinear equation? And I'll pick up in a second here. Okay, hopefully you did stop and you've thought about it and you have a good idea of how each term influences what you think about linearity. And I'll go through and tell you exactly which of those do and which of those don't matter for linearity. So the method I'm going to show you for determining linearity starts off as follows. So we move all appearances of y to the left-hand side, LHS, and others, the ones with no y's in them, to the right-hand side, RHS. And so that looks like the following. We have y times y prime is definitely a y-involved term, and then a 3t squared y also has a y in it, but sine of t does not. All right. Okay, so now I'm going to do something that's a little formal sounding. I'm going to define what's called an operator. And this is kind of like a function, like f of x is a function where you plug in an x value and out pops another number, and we call that number f of x. In this case, define an operator so a function whose independent variable is a function itself. And in fact, the output of it is this operator or function is going to be a function as well. So I'm going to give it the name capital F, and I'm going to use square brackets to remind you that this is a thing that takes in a function and spits out a function. And I'm going to define that operator to be the left-hand side of the equation that I put up in the first step. So that is y prime plus 3t squared times y. What does that mean? So what's the function that I get out? If I plug in the function y of t, out comes the function that is made up of a product of y, the function itself, with its own derivative, and then add to that 3t squared multiplied by y itself again. And that is what I'm going to call the operator, which takes the function y and spits out a more complicated function, which is given by this expression. Okay, so now to determine linearity, an equation, or an operator, I should say, an operator is considered linear oh, maybe I'll give that a green, is linear, provided the following statements are true. F plug in y plus z gives you the exact same answer as f plugging in y and then adding f plugging in z. And so that's one condition. I'll call that condition A. And condition B is that if I plug in some constant number c multiplied by function y, that gives me the exact same output as c times f with y plugged into it. And c is constant, meaning constant with respect to t, and y and z are functions of t. But for simplicity of notation, I've just suppressed the of t. Okay, so if we can do that, then now we have to, now that we have that definition, we could use that definition to determine whether our operator, y times y prime plus 3t squared y, is actually a linear operator or not. So let's check linearity. So let's see. So we take f and we plug in y plus z, and out comes y plus z, that's what I plugged in replacing y in the original definition of the operator, times y plus z prime plus 3t squared y plus z. And so here, when I multiply this out, well, okay, first I get y plus z. And now, when I take the derivative of the sum of two functions, I can just take the derivative of the two parts separately. And that's actually because a derivative operator is linear. In other words, I can do the derivative and then add, or add them and then take the derivative. And the addition property here, A, works for the derivative operator. This is a much more complicated operator, and so we have to do a lot more checking. And so let me continue going here, plus 3t squared y plus 3t squared z. And now I have to multiply out this big binomial, and I get y times y prime plus y times z prime plus y prime times z plus z times z prime plus 3t squared y plus 3t squared z. And now I'm going to group these because I can make an operator looking thing here, y prime plus 3t squared y. Hey, that looks good. And then I can add plus z times z prime plus 3t squared z. That also looks good, and the reason I say that is those two pieces are actually f of y and f of z. But I have some leftovers. And these ones are the problematic terms, oops, not plus, times, that will make this operator not linear. So now we can see that the first two terms actually amount to the same as plugging y into f. And the next two terms, so that's these two are the ones I just wrote down, and these two are the same as f, oops, square brackets, sorry, f with z plugged into it. But then I've got these extra bits that I can't get rid of because this extra bit is not guaranteed by any means to be 0. I can plug any function y and any function z in there, and there's no reason for those things to be 0. So what this means is that condition A has already failed. Now we can check condition B. So let me put an A up here and then a B down here. And now we can say, what is f of c times y? But already it doesn't actually matter. But let's just see if it also fails because of the constant test. So what is this? So here I get y, c times y multiplied by c times y prime plus 3t squared c times y. And now we can see that this gives me a c squared times y prime plus 3t squared cy. And I can pull out a c, which is what I want to do. I want to see if this is the same as c times f of y. But when I pull it out, what I'm left with is a c in the brackets here, because there were two of them. And that's because there's a product of two y expressions, plus 3t squared y. Now, if the c was 1, then I would have f of y in the brackets here. But it's not. And so this is not equal to c times f of y. And in both cases, the culprit in the nonlinear problem here, or the not linear piece, the culprit in the first case, in part A, was that there's a yz prime and a y prime z that was left over, and that came from the product of y and y prime. And in the next case, the problem was, again, the y times y prime. So you'll notice that a 3t squared doesn't really matter that there's a t squared, which looks like a nonlinear term, or the fact that it's a t squared multiplied by a y. Neither of those things were a problem for these two properties. What was a problem is when you had a y multiplied by a y prime. That is what we call a nonlinear term. So it's a nonlinearity in the y parts of this equation that matter.